Hello friends, how are you? Hope you're doing well. In this video, we are going to see the tutorial on how to make this awesome skybox wiggle effect where you can make your skybox wiggle or move in a wavy pattern when you hover with the mouse on the screen. Before diving into the tutorial, if you want to download the project, I have given the link in the description. The link also has the web demo so you can check that as well. Let's dive into the tutorial on how to create this skybox wiggle effect. The first thing you have to do is create a new Unity project with a universal render pipeline. I'll name this as Fluid Skybox Tutorial. I'm using the latest Unity 6 LTS version and let's create this Unity project. Okay, I created the new Unity project and also renamed my scene as Fluid Skybox. Here in the scene, what I want to do first is replace the default skybox with our own custom skybox. But how to change the skybox? You have to go over here and check for this lighting tab. If you don't find this, you can go to the window rendering and find this lighting menu and you can open it. If you go to the environment section, you can find the skybox material. This default skybox material is what rendering this skybox. We're going to create our own custom skybox with a custom shader. So let me create a new folder called shaders. Within that shader folder, I'm going to create my custom shader graph. Since it is a URP platform, I'm selecting URP unlit shader graph. We don't need any shadows from lighting, so we create an unlit shader graph. Let me name it as Fluid Skybox Shader Graph. Then we'll create a material out of this. Just right click and create a material. We're going to assign this material to our Skybox material. Let's see what happens if I drag and drop. Yeah, so it changes to a gray color because that's the default color set in the shader graph. Here in the fragment shader, we are giving a gray color to all the fragments. So if I change this to red color and save the shader graph, the skybox will be red. Now we're going to change our skybox to a custom texture. Let me create a new folder called textures. Here, I already have the texture ready. This is an equirectangular image that is well suited for a sphere map or a cube map. So that will perfectly align with the spherical shape. Let me import this into my Unity project. Once we imported this, and in the import settings of the texture, we have to change this from 2D to cube. Once we do that, and then we just apply it, it will become a cube map. You can also see the preview over here. This will become a cube map, so this can be applied to a skybox like a spherical map. Now we have to render this cube map texture color to our skybox by sampling the texture in the shader graph. Let me maximize the shader graph window by pressing Shift plus space key. We are going to create a node for sampling cube map texture. That node is called sample cube map node. Here it is having two important inputs. One is the cube map and the other is the workspace direction for sampling the cube map. To get the cube map as input from the shader material, here in the blackboard, we're going to create a cube map parameter. I'll name it as cube map text. Then give it as the input to the sample cube map node. But how does the sampling of the cube map actually work? So imagine this skybox as the init sphere. And if we want to know what pixel color has to be rendered onto the sphere surface, we have to know the direction from which we are weaving the particular pixel or fragment. This weaving direction is between the fragment position and the camera position. Since the skybox is theoretically infinitely far away, we can assume that the camera is at the center of the inner sphere. Let's create the direction vector in our shader graph. Create a position node. The position has to be in the world space, and we are going to get access to the camera node. In the camera node, we have this position parameter. We're going to subtract these two so that we'll get the direction vector. Let's also normalize this so that this will work with our assumption of skybox as a unit sphere. Now assign this direction vector to the direction input of the sampling cube map node. So now our texture will be sampled correctly and then displayed as our skybox. So let us save this and then go back to our scene and see what's the output. Okay, so it is still gray because in our material we haven't assigned the texture. So let's assign our cube map texture. Oh yes, we have made our first step in creating our custom skybox shader graph and it's looking awesome. The next thing is, as we see on the demo, the skybox is actually rotating automatically. So we have to make it rotate first and then we can work on the wavy or wiggly the skybox later. So how do we do that? We can simply rotate the view direction vector around the y-axis. So that way our sample pixel on the unit sphere gets rotated. In order to make the shader graph simple, neat and clean, I'm going to put all the rotating logic into a separate HLSL code. For that, you can actually go to your Explorer and then here in the shaders, create a new text file, name it as Skybox functions, and the format should be HLSL. So Unity can make use of this code in the shader graph. Go back to Unity and here I got the HLSL function. Let me open this in the Visual Studio Code. We're going to create a function. Since we are going to do both rotation as well as make it wiggle like a sine wave, I'm going to name it as sinusoidal sphere with an underscore float. This float is going to ensure that the precision of the rendering will be float. And we're going to get the input direction as flow3 in position and the output direction as out position. Since we are treating the skybox as a unit sphere, the normalized vector is also equal to the position on the unit sphere. For example, the vector 1, 1, 1 is a position 1, 1, 1 on a unit sphere, and we're going to transform this position in our HLSL function. Inside the function, let's create a variable float3 position equals L position. Then we add the variable angle equal to time multiplied by rotate speed. This angle value will keep on increasing with time, and we will use this value to rotate the position. Also, don't forget to get the time and rotate speed as input parameter in the function. Now, how to make this position rotate along y-axis by this angle? We have to use a rotation matrix that will transform this position based on the angle. So let's create a separate function, rotate y. This will take float3 position and float3 angle as input. Now create cosine and sine of the angle. So float cos angle equals cos of angle, and float sine angle equals sine of angle. Okay, let's define the rotation matrix. Float3 cos 3 rot mat equals float3 cos 3 and cos of angle, 0, minus sine of angle, 0, 1, 0, sine of angle, 0, cos of angle. If you notice in our rotation matrix, the second row or column is 0, 1, 0. It's like an identity matrix. So the rotation transformation happens only for the x and z components on the horizontal plane, making it rotate around the y-axis. Now we have to multiply this rotation matrix with our position. So float3 rot position equals mul of rot mat, position. Then return rot position. So now we have to call this rot y function in our main function. So we're going to reassign the position to rot y of position, angle. Okay, this will rotate the position around the y-axis. Let's go back to our shader graph. To make use of this HLSL code in our shader graph, we have to create a custom function node, and in the node settings, assign a HLSL code and set the name of the function that will make use of it. The name of the function is nothing but the sinusoidal sphere. Also set all the inputs and outputs, the inputs, time, rotate speed, and the outputs. Now our custom node has the inputs and outputs ready to be assigned. Assign the normalized direction vector to the inputs. For time, create the time node and assign it. For rotate speed, create a rotate speed shader graph property in the blackboard and also assign it to the custom function node. And now take the output of this node, assign it to the direction of our sample Cubemap node, and save the shader graph. So we have transformed the direction vector, and this should make our skybox rotate. So let's play the scene and check. We can see that our skybox is rotating now. We can also change the rotate speed and check the results. Awesome. Okay, the next thing we have to do is transform the position so that it will appear like a sine wave along the horizontal plane or the latitude of the unit sphere. So how do we do that? Let's get the radius of the sphere. The radius of the sphere formula is float radius equals the length of position. The length of the position is going to give the radius of the sphere. Now what we are going to do is simply modify this radius with a sine wave in the horizontal plane. For that, we are going to get the latitude angle in the horizontal plane, and the latitude angle is equal to the tangents of the z and x component in the horizontal plane. In HLSL, it is called arctangent of two components, that is a tan 2 of post.z, post.x. We can now create a sine wave value along this latitude angle. Sine wave equals sine of this latitude angle. And we also want to modify this wavy pattern with some input parameters of frequency and amplitude. So let us get those values as input parameters as well. Float frequency, float amplitude. So we can change the frequency by multiplying the angle by the frequency value, and we can change the amplitude of the sine wave by multiplying the entire value by this amplitude value. We should also change the sine wave based on the mouse input position. So we also get that value as rotate offset input parameter, and we simply need to add this value to the angle. So that way the angle will be changed based on the mouse position. And ultimately the sine wave will appear to be moving left and right. And finally, we can change our radius with our new sine wave. So we have modified the radius, but actually we have to modify the position. The radius is nothing but the length of the position. The position is all three components x, y, and z. But what we need to modify is the position along the horizontal plane, which are only the x and z component. So how do we do that? Let's say position x is equal to radius times the cosine of longitude angle, but we have not defined the longitude angle, so let's define that as well. The longitude angle is nothing but the tan inverse of the y-axis on the horizontal plane. So what is this horizontal plane? The horizontal plane is nothing but the resultant component of the x and z component on the horizontal plane. So the resultant component is nothing but the length of x and z components. So let's do that. Longitude angle equal to a tan 2 of post dot y comma horizontal plane. This HL plane component is the length of the xc vector. That is float 2 of post dot x comma post dot z. This is going to give the longitude angle. Coming back to this formula, multiply radius with cosine of the longitude angle is going to only give the projection on the horizontal plane. But within the horizontal plane, there are two components, x and z. We are interested only on the x components. So to filter the x component, we're going to multiply it with the cosine of the longitude angle. So we'll do the same thing for position dot z component, but since z is perpendicular to the x, we are going to replace the cosine with the sine of latitude angle. Okay, we finally modified the position x and z component of the horizontal plane. So now our sphere should look like a wavy pattern as we expected. So let's go back to our studio graph and add this newly created parameters, frequency, amplitude, and rotate offset. Let us also create those studio graph properties and assign them to our custom function node inputs. Okay, let's play this and see how it actually works. This looks weird. We can change the parameters, the frequency to 3 and the amplitude to 0.15. Okay, so now the skybox looks wavy and it's awesome. Also here we have something called the rotate offset that we earlier told that we will be passing the mouse position as rotate offset, and there may be sine wave move the mouse hover. So the skybox is wiggling, and the only last thing we have to do is, instead of manually rotating this rotate offset, we have to somehow set the rotate offset value to the mouse hover value. So for that, what I'm going to do is I'm going to create a new C# script called skybox controller and assign it to the main camera in the scene. Let's open the script. I'm going to get two public properties. The first thing is public material, target material. The second thing is the sensitivity of the mouse hover, public for sensitivity. Okay, next I'm going to declare two private properties, one for the material property name and the current value of the material property. So let's declare that as well. The property name that we are going to set is the rotate offset. In the start, what I'm going to do is just get the current value of the rotate offset for the material. Current value equals to target material dot get float property name. And in the update, I'm going to get the mouse movement and then update the current value and then set this current value to our material property. Let's get the mouse hover moment, float mouse moment x equal to input target axis mouse x. And we also need to multiply by sensitivity, and again we'll multiply by time dot delta time. This time dot delta time will keep the mouse moment sensitivity the same across all platforms. Then we will add the current value with the mouse moment x, and finally we will assign the target materials property with this current value. Okay, so that's it. So let's go back to our project and assign the target material here. Target material is our current fluid skybox material. Assign that, and let's keep the sensitivity higher, like 20. Okay, and let's play it and see if it works. There is an error. This error shows that I have not added the legacy input system to my player settings. Go to the player settings, and in the player settings, go to the other settings and set the input handling as both. So the Unity will restart now, and the error should be fixed. Okay, the Unity is open. So let's play it and see whether our mouse hovering is working. Yes, it's working, but the sensitivity is very low. So let's increase the sensitivity to like 50 maybe. Yeah, it's working, guys. Working amazingly. The skybox is wiggling. Maybe I will increase it to 70. The skybox is wiggling, that you can see. Wow. So let me play it in full mode, and it's looking so cool. So this is how you will actually make the awesome skybox wiggle effect in Unity. So that's it for today, and if you like the video, please click the like button. For more tutorials, please subscribe to my channel. I'll see you in the next video. Bye bye. Thank you.